Okay, so good morning. So I'm going to give a talk today on spin orbit coupling as a source of rich and complex magnetic phenomena. Sorry. So the outline of the talk is the following. I'll give a brief introduction on spin orbit coupling, and then I'll mention one example in which spin orbit plays a relevant role in a class of ferroelectrics, Rashford semiconductor, but I'll touch very briefly on that. And then the rest of the talk will be actually focused on exotic spin texture into the magnets, which is the topic we've been recently working on. Okay, so first an introduction on what we do and where we are. So we actually work in let me see. Yes. So we work in the central part of Italy, in Chieti, close to the coast. I lead a very small group in Chieti. And actually the class of materials that we've been working on is rather diverse. It ranges from oxide to organics to surfaces and recently on 2D magnets. We are basically a density functional theory group, which means we do first principle simulation. But also we benefit a lot from symmetry analysis and model Hamiltonian studies. So our expertise is basically to start from electronic structure theory, but then focus on the microscopic mechanism. So we are really interested on understanding, which is the source of, the origin of the phenomena that we actually see. And if we understand the microscopic mechanism, then of course we can optimize the effects for specific purposes, and eventually we can also do materials design. So actually, the interest that we are generally addressing are the class of ferroid material. Ferroid material are ferromagnet, ferroelectric, and ferroelastics. And we are interested in the cross-coupling phenomena. So those materials that show an interplay between dipolar degrees of freedom and spin degrees of freedom, and also deformation. So I've been working a lot on multiferroics, so those materials which show at the same time ferroelectric order and ferromagnetic order or antiferromagnetic order. Then recently we investigated the coupling between spin orbit interaction and ferroelectric material, which is something I briefly touch on. And then recently, we touched the interplay between magnetism and topology. So in this respect, we addressed skyrmionic spin texture, which is what I will discuss later on. So spin orbit coupling. What is spin orbit coupling? So it's a relativistic interaction. It's a coupling of the orbital momentum and spin momentum, which you can see here. So it's a scalar product of sigma dot L. And in most of the material, so avoiding very heavy material like uranium or platinum, it's considered to be a small interaction. So if you want to know how small, if you compare the scale of spin orbit coupling compared to other relevant energy scales, such as the scale of hybridization, well, that is a couple of orders small. So it's like 1 to 10 electron volt for a bandwidth and hybridization. But it's of the order of 1 to 10 to maybe 100 milli-electron volts for spin orbit coupling. So it's kind of small. However, it can give rise to many interesting phenomena. So actually it can be very relevant in both non-magnetic solids and magnetic solids. So all the topological matter actually in almost all cases is based actually on spin orbit coupling. And also in other phenomena such as spin valley coupling or Rashford Ferroelectrics phenomena, spin orbit is actually the source of them. And of course it's relevant in magnetic solids. Of course it drives magnetic anisotropy and also drives other interactions such as Silvia and anisotropic exchange, which I will discuss today. So let me briefly touch on the Rashford Ferroelectrics. So if I have a ferroelectric material, so ferroelectric material is a material that shows at the same time, shows a permanent and switchable polarization below a certain Curie temperature that can be actually switched in a permanent and non-volatile way. So if I couple ferroelectricity with a material that has at the same time a large spin orbit coupling, then I can have a Rashba effect. And it's not a conventional Rashba effect as it happens in many other materials which lacks inversion symmetry. I should recall, of course, that any ferroelectric material, since it has a definite polarization, breaks inversion symmetry. So Rashba effect is always allowed by symmetry. But in case the effects are rather strong, then this is the typical band structure that one would get. So if you start from a simple free electron model with a parabolic band structure, then the Rashba coupling would split to bands. But in ferroelectrics, you have an additional functionality. So the polarization, actually, which can be tuned with an electric field, actually drives the spin texture. So if you have, for example, polarization pointing up, ferroelectric polarization pointing up, then the spin texture, which is shown here by arrows, so for example, in the inner branch of the Rashba bands, the spin texture would be clockwise, and the outer branch would be counterclockwise. If you now switch polarization, so you apply an electric field which is opposite, actually one can also permanently and non-volatile way switch the spin texture. So you basically achieve the electric control of spin degrees of freedom. So that was the concept which we actually put forward back in 2013 by first principle calculation in germanium telluride, which is one of the simplest ferroelectrics known. Actually, it's a distorted rock salt with a displacement between the center of mass of tellurium and germanium sublattice. And we actually showed by means of an initial calculation that if you switch the displacement, which is shown here, actually we can do in the computer just by moving the relative position of the germanium versus tellurium sublattice. If we do that and we calculate the spin texture, so here you see a constant energy cut of the band structure, on top of which we can calculate the spin expectation value, which actually gives us the spin texture, which is shown here by these arrows. So you see here the arrows, and of course in the previous slide I added a very simple picture with parabolic band structure. So if you cut a parabola, then of course you see an inner circle and an outer circle. But here I have a complex band structure with magnetization effect. So actually the circle turned into a star, which is what you see here. However, the physics is more or less the same. So you see the spin texture always perpendicular to the K vector, which is typical of Rashba. And the important thing is that if you switch polarization, you'll see the spin texture changing. So here it circles clockwise, and here with opposite polarization, it will circle anti-clockwise, which is actually what we expected in the beginning. So actually after the first principle prediction, actually the confirmation came from experiment 3 years later. And actually the situation is a bit more complex because on top of a bulk Rashba effect, you have a surface Rashba effect. But actually germanium telluride is really shown to be a material which has a large Rashba effect, which is coupled to polarization. So let me now move to the topic of the talk, actually. And so I want to talk about 2D magnetism, which is one of the topics at the center of big interest. The hype started in 2017, 2016, with the discovery of ferromagnetism in chromium-3, monolayer and bilayer. However, the understanding is not, yet complete. There is still, room for improvement. And actually, the first thing that comes to most people's mind when discussing 2D magnets is actually the Bromine theory, which says that if I have an isotropic model, such as the Heisenberg model, I cannot have any finite range order, so that there cannot be any long range order if I only have isotropic interaction, which again points pretty much to the importance of spin-orbit coupling, which breaks this isotropic interaction because it's an anisotropic effect. So spin-orbit is particularly relevant in 2D magnets. Okay, so the class of material that we study are nickel halide, So we chose a monolayer, actually of nickel chloride, bromide, and iodide. So in nature, they are van der Waals crystals, and they are corner shared octahedra, with having at the center nickel and the corner iodide. The nickel, actually, the peculiarity of this material is that nickel forms a triangular lattice, which will be very important for what comes next. The octahedra are rather slightly compressed along one of in this direction, so perpendicular to the faces. So if I now move from chlorine to bromide to iodide, actually spin orbit will be increasingly stronger, and so I expect large spin orbit in iodine and rather small in chloride. So this material has rather localized magnetic moments, about 2 Bohr magneton, and also a small induced moment on the halide. And it is known from old characterization that the magnetism is very complex. So in the crystal, in the bulk, there is a complex helix, which was pointed out at the end of the 80s. So let me briefly recall a bit about frustration, because that will be very important for the remaining part of the talk. So what is frustration? What do I mean by frustration in magnet? So if I have a triangle and I have an antiferromagnetic coupling, then of course if I start with the spin, this will be up, but then the third spin doesn't know what to do, because if it's pointing up, then this interaction will not be happy. If it's pointing down, then this interaction will not be happy. So in the end, the system will try to find a compromise in which more or less all the interactions are happy. So actually the ground state will be that oriented, with spin oriented around 120 degrees. And frustration are actually strongly linked to the kind of lattice on which the magnetic sites sit. So there are particular lattices such as the Kagome and pyrochlorine 3-dimension and triangular lattices that are particularly prone to the frustration effects. But even if you have a small, simpler system, so you have a spin chain, and if I have, for example, a ferromagnetic interaction in first nearest neighbor, but an anti-ferromagnetic interaction in second nearest neighbor, then this is also kind of frustrated material, right? Because of course it cannot be, all the interaction cannot be happy at the same time. And actually the ground state, so if you have Ising spin, so there is a strong anisotropy, actually the ground state is found to be up, down spin chain. But if you have more, isotropic spins, so you can rotate actually in all directions. Actually, the ground state is a helix, which is shown here. Okay, so let's start with the characterization of our system. We choose nickel iodine for the moment, and so we start with the simplest Hamiltonian, Heisenberg Hamiltonian. So in our case, well, by DFT one can infer the exchange coupling constant at first, second, third nearest neighbor by mapping total energies on this model. And what we find is that we have a strong ferromagnetic interaction, a second nearest neighbor interaction which is basically negligible. And what is also peculiar is that the third nearest neighbor is very strong and anti-ferromagnetic. So what happens if I try to satisfy all these interactions on my lattice? My first interaction will be ferromagnetic, and then my second one will be anti-ferromagnetic, right? So I immediately see that I have some frustration in my system, because this spin would like to point down for the anti-ferromagnetic with the central one, but would also like to point up for the ferromagnetic with this first nearest neighbor, right? So you expect somehow that the frustration will happen in this material and will lead to expected at least non-collinearity. However, there is another ingredient, because we learn in magnetism courses that the Heisenberg term, Heisenberg Hamiltonian, is the basis, and it actually is, but on top of this there are other terms. So actually, I should not consider only isotropic spin, but I should consider an exchange matrix. So my most general Hamiltonian should be written in this way. So I have a spin at side I, spin at side j, and they are coupled to a matrix. So if I have a 3 by 3 matrix, so even from the mathematical point of view, I can always decompose my exchange matrix in an isotropic term, which I can take the trace of this matrix. This can be considered isotropic. And then the remaining part, I divide it in anti-symmetric and symmetric part. So this can be done even, for whatever matrix from the mathematical point of view. But of course, we're physicists, so we want to understand, what this mathematical decomposition actually means. And of course, they have a meaning. So this isotropic is what is generally labeled as Heisenberg term. The anti-symmetric is actually what people call Cefalù-Cesky-Moria interaction, which is the vector product of the spins. And there is an additional term. So this symmetric part, which is generally labeled as an isotropic exchange. So Heisenberg, what does he do? Heisenberg, of course, tells us whether the spin want to be parallel or anti-parallel, but it doesn't matter, suppose they favor ferromagnetism, it doesn't matter whether they lie like this or like this. So it's the same, right? It doesn't tell me anything about space, the direction in space that the spin want to reach. Cefalù-Cesky-Moria tells me what? It tells me, of course, it's a vector product, so the spin will try to count, but they try to count in a certain sign, right, which is actually linked to the sign of the Cefalù-Cesky-Moria vector. So this distortion is not equivalent to this one, and there is one that is favored compared to the other. And an isotropic exchange tells me what? This is like a two-side anisotropy. So it will tell me, again, how the spin want to align, parallel or anti-parallel, but also will tell me whether the spin want to be like this or like this. So it's a two-side anisotropy. Okay, so in ours, both Cefalù-Cesky-Moria and anisotropic exchange are actually linked to spin-orbit coupling. So the heavier the elements I have in my system, the strongest the effects will be. And then I will, the other thing I would like to mention is that in our system, the Cefalù-Cesky-Moria is 0 because we have a centrosymmetric system. So the inversion symmetry is there, and as such, Cefalù-Cesky-Moria is forbidden. Okay, so by symmetry, actually, the form of the matrix is such that it has 0 here, and then 0 here and here, and then it has diagonal term, and only one of diagonal term. This is a symmetric matrix, so I have only one of diagonal term. Okay, so what happens again if I try to estimate this parameter from first principle? Then what you see, what you get is the following. So in nickel chloride, basically, you have your exchange coupling constant, which is basically xx is equal to yy is equal to zz, and there's basically no off-diagonal term. So this is a pure Heisenberg magnet, right? But if you start, increasing spin orbit, then you expect that an anisotropic term will grow, and this is actually what you see. So nickel bromide is slightly heavier, and you start seeing off-diagonal term. And off-diagonal term are even, stronger in nickel iodide. So you see that even along the diagonal, you have JXX, which is different compared to JYY and JZZ. And also you see that the off-diagonal term is really large. So it seems that it's very important, not the spin-orbit coupling of the transition metal, which is constant here, it's always nickel, but it's very relevant the spin-orbit coupling of the anion, of the ligand, because iodide actually shows much more anisotropic effects than chloride. Okay, so now what we did actually is use this exchange matrix and also add a single ion anisotropy term, which we can also estimate from first principle, and we use this Hamiltonian in a Monte Carlo approach. This is to explore, finite temperature and also larger scales simulation, which we cannot afford by DFT. So we did Monte Carlo and we explored the spin texture in our system. Also, let me mention what is the notation that I will follow in the remaining slides. So if I have, suppose I have a magnetic vortex, then I plot the in-plane spin texture by arrows, and I plot the out-of-plane spin texture by colors. So for example, here I have my spin along Z, so this will be like a red circle, and then this arrow actually will tell me the in-plane projection of the spins. Okay, so if I now do Monte Carlo simulation for nickel bromide, what do I see? I basically see, so I expect frustration, right? Because I have a strong J3 over J1, so I expect a complex system, which is actually what I see here. This is a specific heat. I see a transition, the temperature are rather low. If I do the structure factor, I see 2 peaks, which tells me that basically I have a spin helix here, which is actually what I expect, because I have, J3 over J1. I know that it gives a spiral. Actually, here it's a helix which is quite complex, so it's a combination of spin spiral and spin cycloid. However, when I do nickel iodide, we basically were rather surprised to find this. So we basically, even if we zoom, we realize that we have a very complex spin texture. And so, what is this? So we went back studying skirmion, which is something we didn't have experience on. So briefly call, probably there are many experts in the audience about skirmion, so I'll be brief on that. It basically skirmion are topological object that have a complex spin texture with a specific topological nature. Basically there are many kinds of skirmions with different rotational sense of the spin going from the center to the edge. And also, what is rather common in all the skirmion-based material is a complex phase diagram. So here I show one, they more or less look almost all the same. So basically, the ground state is actually a helix. So you start from something that was already complex, and then you apply a magnetic field, and then you end up in a region where the skirmion usually happens. So what generally is observed is actually that the skirmion are driven by magnetic field. And in most cases, they actually are driven by Cefalù interaction, which is a chiral interaction. So the way that people characterize actually the various kinds of skirmion, which you can see here, I have skirmion and anti-skirmion, is actually through the topological charge. So the topological charge actually, here I have a complex magnetic distribution, so the magnetization is actually a vector field with many different directions, and I can estimate in the continuum model my topological charge in this way. But of course, we have discrete spins in our Monte Carlo simulation, so we had to choose a corresponding discrete formulation for our topological charge, which is actually shown here. So the main ingredient of this topological charge is actually the spin chirality. So you take, in our case, we have a triangular plaquette with spin M1, M2, and 3. So we evaluated this scalar spin chirality and sum over the lattice. So you can immediately see that for scalar spin chirality to be non-zero, you actually not only need non-collinearity, but you need non-coplanarity. This is actually very important to have a non-trivially topological object. So the topological chart gives you a measure of the wrapping of this magnetization actually on the surface of a unit spin. So if I have a Q equal 1, then it only wraps once. If I have Q equal 2, it wraps twice, and so on and so forth. We evaluated actually the topological charge in our system, and actually what we discovered is that this is indeed a skirmion lattice. So the topological charge is actually equal to 2 for each of the topological objects. We have 6 here because we have 3 topological objects in our unit cell. And we have a peak at around 20-30 Kelvin. So this is presumably the transition temperature. Okay, so This is quite peculiar system, right? So we have a topological ground state, so it's not driven by any magnetic field. We have it as a ground state. But to our knowledge, this was the first example we added into the magnet when we wrote the paper. It's not driven by Cefalù-Moria because there's no Cefalù-Moria interaction. And we have a fermion lattice, so we don't have any single fermion. Here we really have a lattice with a rather small periodicity, so it's about 8 times 8 of the lattice periodicity. Okay, so since the isolated fermion are rather common, let me just show you one slide on the connection between a single object and a lattice. So I start from something which has a Q equal to an anti-fermion. This is an anti-fermion with Q equal 2, and I try to put all the anti-fermion in a lattice, and I try to reduce the lattice constant. So what I actually end up with is actually, I have a core at the center, and then I have vortices with opposite circulation. So actually, of course, in our system, we really have few spins. So everything here happens on a much smaller scale. These are really nanometric scales. But the picture, basically, you can actually understand this in terms of this more regular pattern that I'm trying to show here. The size of the fermion is actually driven by the ratio between the J3, the third neighbor nearest coupling, compared to J1. Okay, what happens under magnetic field? So if I apply magnetic field along the Z direction, so perpendicular to the layer, actually I end up in a situation which is more common. I don't have any more an anti-fermion, but I have more like a fermion. Okay, so which is what is shown here. And in fact, if I evaluate the topological charge again as a function of the magnetic field, I basically have very sharp transition. So I start with 0 field, then I have Q equal 2, then I apply a field, and at a certain point there is a continuous, a discontinuous jump to Q equal 1, so normal fermion, and then for very large field I have Q equal 0. So of course the system will be in a ferromagnetic state. So one can draw again a phase diagram. Here the temperatures are always rather small. It's like 30 Kelvin, which is perfectly consistent with the fact that I have a frustrated system. In general, it's really hard to have a frustrated system at room temperature unless you start with really strong J. But here the temperatures are around 30 Kelvin. Okay, so let's investigate. I said in the beginning that we always want to understand a bit more about microscopic mechanisms. So let me do that. Okay, I now have my symmetric matrix. So I know my symmetry is done like this, but I can diagonalize. It's a symmetric matrix. I can always do that. And I can actually look at the eigenvectors and see how they are aligned actually with respect to my physical position of the atoms. And then what we infer is basically that there is one of the eigenvectors is actually pointing along iodine-iodine ligand, one is pointing along nickel-nickel bond, and the third one is perpendicular. So of course the geometry of the system is a bit complex, but you should imagine that you have non-coplanar plaquette. I call a plaquette an arrangement of 4 ions. So this is my plaquette, nickel, iodine, nickel, iodine. And these plaquettes are actually tilted one with respect to the other. And so since actually the eigenvector direction will be those along which the spin will try to align so as to gain energy according to the anisotropic exchange, the thing is that these plaquettes are actually arranged in a non-coplanar way. So the different plaquettes on my lattice will drive the system towards having a different orientation. So it will again be a source of frustration because this, the nickel on one plaquette will have a different orientation if it's, sitting on the plaquette of right and the plaquette of left. So in general, there will be a strong frustration in the system. And in particular, they will be, the favored direction will be non-coplanar. So this is basically the origin of what we actually see, or a main origin. Of course, it's also important that we start already from a frustrated system driven by J3 over J1. But this anisotropic exchange is actually strongly giving rise to the topological behavior that we see. So one final thing I would like to mention, can we have this in chromium-I3? Chromium-I3, as you all know, is a very much studied material. And so we wanted to, and it has iodide, so one can, think that actually an isotropic exchange play a relevant role also there. And it actually does. So people have actually estimated the exchange matrix. And so actually even there are off-diagonal term, and also the diagonal term are not always the same. So this is far from a Heisenberg system. However, the frustration given by J3 over J1 is not there. And it's actually not there because, the crystal lattice is actually different in chromium-I3 and nickel-I2. Chromium-I3 is a honeycomb lattice, which means that here it's not a triangular lattice. So once every 6 transition metal there is a hole. Actually, this hole is very important in our case to mediate the third nearest neighbor interaction. So since in chromium-I3 you basically have a hole here, the J3 will be very small. So you lack basically frustration given by the J3 over J1 ratio. So you could actually have an isotropic exchange in chromium-I3, you do have it, but since you lack the initial frustration, then you don't expect any skirmion driven by anisotropic exchange, so similar to what we have in nickel-I2. So that the systems are very different because of the coordination in the end, because one is a honeycomb lattice, the other one is a triangular lattice. Okay, so let me come to the conclusion. So we had a higher order anti-skirmion in nickel-I2 monolayer. Here we only looked at monolayer. So there is no B field needed, and it has a fixed chirality. So we always have the same fixed chirality. Is the first example in 2D magnet, and we think that what we see actually from Monte Carlo simulation actually has its root on the strength of the anisotropic exchange. We have a lattice, so it's a rather small lattice periodicity. And also if we apply a magnetic field, then there are other topological transition to normal skillman phases. Of course, this was the the initial part of the story, but there are many open questions actually that one needs to answer. The first is why this nickel-I2 has this large anisotropic exchange. Is it common to other 2D magnets? That is quite important, I think, because so I would like to understand why nickel-I2 has this large anisotropic exchange and what actually drives a large, and it's not only spin-orbit coupling. So there are certain material which we lack an understanding of that show an anisotropic exchange. So it could also happen, that nickel-I2 has many competing energy scales. So it could also happen that actually this state that we predict is actually not realized because there are so many competing effects here. But what I'm convinced is that this mechanism actually works. So one needs to understand, when it's large and explore those systems to really find, explore these potential topological effects that arise from an isotropic exchange. Also, we looked at monolayer, but we didn't look at bilayer, trilayer, and even we didn't look at the bulk system. So one should do that because, of course, it's hard to also experimentally exfoliate just one layer. Very often they do 2 layer or bilayer or trilayer. So it would actually be very nice to explore also the other, bilayer or trilateral, the interlayer coupling, which is okay, you expect it to be small, but all the interactions are small here. Many of the interactions are actually small, so that the balance can be tipped in, one of the one direction or the other, even if you have interlayer interaction. The other thing that we are interested in is the magnetoelectric coupling. There could be, some magnetoelectricity in this system that was observed in the crystal, and one should, explore whether, this magnetoelectric and multiferroicity actually still, survives in the monolayer. And of course, we are theorists. We made a prediction, but it would be very nice if experimentalists could actually measure it. So with this, I would like to conclude, and I want to thank you for your attention, and I'll leave you with the reference in case anybody of you is interested in reading our work.